A transverse load does two things inside a beam. The bending moment creates longitudinal normal stress, while the shear force creates transverse shear stress. Imagine a stack of loose cards bending together. If the cards are not bonded, neighboring layers slide. A solid beam prevents that sliding by developing longitudinal shear between its layers. On perpendicular faces, an equal complementary shear stress appears for rotational equilibrium. So, beam shear is not merely a vertical force divided by area, it is the internal mechanism that keeps the layers acting as one beam. Take two nearby cross sections separated by delta x. Their bending moments are m and m plus delta m. Because the bending stress is sigma x equals my over I, the longitudinal stress distribution changes from one face of the slice to the other. Therefore, the resultant longitudinal force in any selected portion of the cross section also changes. That imbalance must be balanced by a horizontal shear force along the cut surface. The differential beam relation is dm by dx equals v, subject to the chosen sign convention. This is the bridge from changing bending moment to transverse shear. Select the area A prime above the level where shear is required. Its first moment about the neutral axis is q equals integral over A prime of y dA, or A prime times y bar. On the first face, the longitudinal resultant is the integral of my over I dA. On the second face, replace m by m plus delta m. Subtracting gives delta h equals delta m over I times q. Divide by delta x and use delta m over delta x equals v. The result is shear flow q equals vq over I. Shear flow has units of force per unit length, such as newtons per millimeter. If the section has local width b at the chosen level, the average shear stress across that width is tau equals q over b. Therefore, tau equals vq over ib. Here v is the internal shear force, q is the first moment of the selected area, I is the second moment of the complete cross section about the neutral axis, and b is the local material width at that level. Do not replace b by the maximum width unless they are the same. Also remember that v over a is only an average reference value. The actual distribution comes from bq over ib. For a rectangle of width b and depth d, choose the area above a horizontal level by measured from the neutral axis. Substitution into vq over ib gives tau of y equals 6v over bd cubed multiplied by d squared over 4 minus y squared. This is a parabola. Shear stress is 0 at the top and bottom free surfaces and maximum at the neutral axis. The maximum is 3v over 2bd or 1.5 times the average stress v over b. The stress equals the average at y equals plus or minus d over 2 root 3. For a solid circle, the local width changes with height, so both q and b depend on y. Evaluating the circular segment gives tau equals 4v over 3 pi r squared multiplied by 1 minus y squared over r squared. Again, the curve is parabolic in y. The maximum occurs at the neutral axis and equals 4/3 of the average stress. At y equals plus or minus r over 2, the local shear stress equals the section average. The zero stress at the boundary is also physically required because the curved surface is free. A triangular section reveals an important lesson. Maximum shear need not occur at the neutral axis. Measure A from the apex toward the base. The neutral axis lies at 2h over 3 from the apex, but the derived stress is proportional to y times h minus y. Its maximum occurs at y equals h over 2. Thus, the maximum lies away from the neutral axis. Its value is 1.5 times the average stress, while the stress at the neutral axis is 4/3 of the average. Geometry through both q and the local width controls the answer. For a symmetric diamond with half depth h, the local width grows toward the neutral axis and then reduces. In the upper half, tau equals v over b h cubed multiplied by h minus y and h plus 2y. Differentiation places the upper maximum at y equals h over 4. Symmetry gives another maximum at minus h over 4. Each peak equals 9/8 of the average stress. At the neutral axis, the stress falls slightly to the average value. This double peak distribution is a useful reminder that the neutral axis is not automatically the location of maximum shear. In an I section, the local width is the flange width near the top and bottom, but becomes the much smaller web thickness in the middle. The first moment Q varies continuously. Therefore, the shear flow Q equals VQ over I is continuous across a sound flange-web junction. But tau equals Q over B increases sharply when B changes from the wide flange to the thin web. The maximum occurs in the web at the neutral axis. Engineers often say the web carries most of the shear, commonly around 80 to 90% for typical proportions, but the exact shear depends on geometry. Compare equal average stress values. A rectangle reaches 1.5 times average. A solid circle reaches 4/3. A triangle also reaches 1.5, although its maximum is not at the neutral axis. A diamond reaches 9/8 at two symmetric points. These ratios are not correction factors to be guessed. They emerge from Q divided by local width. The boundary must have zero shear traction where the surface is free, and the integral of tau over the area must recover the internal shear force V. Stress also creates shear strain. In linear elasticity, gamma equals tau over G, where G equals E over 2 times 1 plus Poisson's ratio. Classical Euler-Bernoulli beam theory neglects shear deformation and works well for slender beams. Short or deep beams can deflect noticeably because of shear, so Timoshenko beam theory includes it. A shear correction factor converts the non-uniform stress field into an energetically equivalent uniform model. Common values are 5/6 for a rectangle and 9/10 for a solid circle. The formula is most direct for prismatic, linearly elastic beams with small deformation and a load passing through a symmetry axis or the shear center. If the load misses the shear center, bending and twisting occur together. The assumption that shear stress is nearly uniform across the local width is best for narrow webs and thin-walled regions. Near-point loads supports whole swell toes and abrupt changes. Three-dimensional stress concentrations matter. Their refined analysis or finite elements may be needed. Shear flow is especially useful for built-up beams. If connectors are spaced by S, the longitudinal force transferred over one pitch is Q times S. When n identical connector lines share that transfer equally, the force per connector is Qs over n. This relation designs nails, bolts, rivets, screws, and intermittent welds. At a free edge, Q becomes 0 and therefore Q is 0. At an interface, always define exactly which area is being transferred and how many connection lines share the force. Consider the box section shown with outer dimensions 112 mm, inner dimensions 76 mm, nail spacing 44 mm, and shear force 2.5 kilonewtons. For the top board, A prime is 76 times 18 square millimeters and its centroid is 47 millimeters from the neutral axis. The complete second moment is 112 to the fourth minus 76 to the fourth divided by 12, giving 10.33 million millimeters to the fourth. Hence Q is 15.56 newtons per millimeter. Over one pitch, the total transfer is Qs. Two symmetric nail lines share it, so each nail carries 342.25 newtons. Now take a built-up I section, 200 millimeters wide, 300 millimeters deep, with 50 millimeter flanges and a 50 millimeter web. The shear force is 2 kilonewtons. For the entire top flange, Q equals 10,000 times 125 or 1.25 million millimeters cubed. The complete I is 350 million millimeters to the fourth. Therefore, the total shear flow transferring the top flange into the web is 7.14 newtons per millimeter. If two identical glue lines share it equally, each line carries 3.57 newtons per millimeter. Stating both the transferred area and number of glue lines removes ambiguity. The complete workflow is now clear. Find the internal shear force V, choose the level of interest, compute Q for the area on one side of that level. Use I for the complete section and B for the local width. Calculate Q equals VQ over I, then tau equals Q over B. Check zero traction at free boundaries, recover V by integrating stress over area, and inspect any sudden width change. For connections, use Q times spacing divided among the actual connector lines. With these checks, beam shear becomes a physical, visual, and reliable design tool.